A vast and infinite universe has always held secrets beyond our wildest imaginations, and often these enigmas prevent the sharing of information crucial to the advancement of science. Recently, the most advanced telescopes have detected a phenomenon that defies all logic, a cosmic mystery that has left scientists around the world perplexed. Findings from the James Webb Space Telescope have called the Big Bang theory into question. Joel Ron takes a deeper look at this telescope's latest discovery, which has revealed the shocking disappearance of 900 trillion stars. The $10 billion James Webb Space Telescope has been operational in space for over 2 years, but the results already prove that its investment has been worth it. The telescope far surpasses Hubble, providing unprecedented views of deep space. In July 2022, James Webb began exploring extremely long wavelengths coming from distant galaxies, detecting radiation outside the visible range known as redshifted ultraviolet. The telescope has revealed astonishing details that were beyond our expectations, showing areas of space that Hubble could not observe. Disturbingly, however, James Webb has discovered the unexplained disappearance of 900 trillion stars in the vacuum of space. This finding raises disturbing questions about how these stars could have disappeared without a trace. Each new piece of data adds an air of mystery and concern. In a surprising observation, the James Webb Telescope has detected the disappearance of trillions of stars without a trace. The question is, where have they gone? There are two main theories about this phenomenon. The first suggests that the stars are still present, but their death could have been accompanied by a lowered luminosity, perhaps hidden by dust, or that they have simply collapsed into black holes without going through a supernova stage. The second theory is more alarming. It could be that the universe is in a process of disappearance that we cannot stop. Almost a century has passed since scientists theorized that the universe was expanding and that the most distant galaxies appear to be moving away from us at an ever-increasing speed. Expansion does not mean that galaxies are physically moving through space, but that the fabric of space itself is expanding, leading to galaxies moving away more quickly. This model, which has been dominant since the 1920s, has recently been revised. Only 20 years ago, it was discovered that this expansion is accelerating. As time goes on, galaxies are moving away from us at an ever-increasing speed, becoming unreachable even if we were traveling at the speed of light. When we look at the stars whose light has traveled for 100 years to reach us, we are seeing that star 100 light-years away. However, when we look at a galaxy whose light has traveled for 100 million years, we're not looking at a galaxy that is 100 million light-years away. In fact, that galaxy is even farther away. The reason for this is that on larger scales, such as galaxies and clusters, the expansion of the universe plays a major role. The longer it takes for light to reach us, the farther away the galaxy is due to the expansion of space. This phenomenon manifests itself as a red shift. As light passes through expanding space, stretches and changes its wavelength. If the universe were not expanding, the wavelength of the light reaching us would be constant. But due to its expansion, the wavelength stretches, causing the light to be redshifted. The significant red shifts we have observed in the most distant galaxies strongly confirm that the universe is expanding. However, our task goes beyond simply verifying this expansion. We can use the information gathered to understand how the universe has changed over time and what it is made out of. When light from a distant cosmic source travels through the expanding universe, its wavelength is stretched, producing a red shift. This effect is more pronounced for objects that are farther away since their light has been traveling for much longer. By measuring the red shift of various sources at different distances and comparing their size and intrinsic brightness to what we can observe, we can reconstruct the full history of the universe's expansion. In addition, the way the universe expands is determined by the different types of matter and energy present in it. This allows us to learn about its composition. Approximately 68% of the universe is made of dark energy, equivalent to a cosmological constant. 27% is dark matter and about 4.9% is protons, neutrons and electrons. Only 0.1% is made of neutrinos and antitrinos and 0.08% is photons. No exotic entities, such as cosmic strings or textures are. Knowing these components with such precision allows us to apply the laws of gravity, according to Einstein's theory of general relativity, to predict the future fate of the universe. Doing so, we discover that the universe is dominated by dark energy. Finding implies that galaxies that are not gravitationally bound to us will eventually move away at an ever-increasing rate. As the universe continues to expand unchecked, the distance between us and those galaxies will increase, making them appear to be moving away at an increasing speed. This leads to an even more disturbing conclusion. At a critical distance, the fabric of space itself expands the distance such that a photon leaving our galaxy for a distant galaxy will never reach us. The expansion rate of the universe is so rapid that distant galaxies are becoming unreachable to us. Even if we could travel at the speed of light, although those galaxies are only 18 billion light-years away, the overall expansion is still increasing and the density of matter and radiation continues to decrease. Our observable universe is about 46 billion light-years. If we consider that all regions of space contain an even number of galaxies, only 6% of all galaxies in the current universe are accessible to us. This means that even if we were traveling at the speed of light today, we would be limited to exploring only a small fraction of the universe. Furthermore, between 20,000 and 60,000, stars go from reachable to unreachable every second. Although the light emitted by these stars a second ago will eventually reach us, the light they emit in the present never will. This fact is unsettling, but it also reminds us of how precious every moment is. From a more optimistic perspective, this reality reminds us that if we ever want to travel beyond our local group of galaxies, which includes Andromeda, the Milky Way, and about 60 satellite galaxies, every second that passes is a lost opportunity. Of the estimated 2 trillion galaxies in the current universe, only 6% are still accessible from the Milky Way, and this percentage is still decreasing. This means that 94% of the galaxies in our observable universe are already out of reach due to the accelerated expansion caused by dark energy. As time goes on, every galaxy outside our local group is destined to move even further away. Unless we develop the ability to travel to other groups and clusters of galaxies, humanity will remain trapped in our local group, and our ability to send or receive signals from the various parts of the vast cosmos will fade away. The accelerated expansion of the universe is relentless, and the gravity we possess is not enough to counteract it. The universe is constantly expanding, and unfortunately there's nothing we can do about it. As we reflect on the implications of the universe's accelerated expansion, it becomes increasingly clear that we are living in a cosmological window of opportunity. This era where vast cosmic structures are still visible and accessible to us is temporary. future civilizations, millions or billions of years from now, may find themselves in a universe that appears empty, dark, and devoid of the grand galactic tapestry we currently observe, without access to cosmic background radiation or redshifted light from distant galaxies. Their understanding of the universe's origin and evolution could be severely limited. This potential future underscores the urgency of present-day cosmological. The data we gather now may one day be the only record of the universe's large-scale structure and history. In a very real sense, we are the cosmic archivists of our time. Can we outsmart the universe? Despite the apparent inevitability of isolation due to cosmic expansion, there is a growing conversation in the scientific and philosophical communities about whether it might be possible to overcome this. One speculative idea involves advanced civilizations creating gravitationally bound megastructures, vast collections of stars and resources, consolidated into a single gravitational system, preserving a portion of the universe for long-term sustainability. Such structures theoretically envisioned as galaxy farms or stellar arcs would cluster resources in ways that remain resistant to cosmic isolation. Another idea involves technology beyond our current imagination, such as faster than light travel, wormholes, or manipulation of space. While these remain purely theoretical and may defy the known laws of physics, history reminds us that many of today's certainties were once impossibilities. However, even within the current framework of general relativity, it's possible to consider ambitious projects like intergalactic arcs, generational spacecraft designed to reach nearby galaxy clusters before they cross the event horizon of accessibility. If humanity begins such missions in the next few millennia, it might still reach galaxies outside the local group. The fate of information and legacy. One of the most profound consequences of the universe's expansion is the loss of information. As galaxies disappear from view, so too does any opportunity to study their structure, evolution, or even civilizations that may have existed there. In a universe where 94% of all galaxies are already receding beyond reach, the need to preserve knowledge and legacy becomes vital. Space-based data archives, possibly encoded on interstellar probes, or artificial satellites placed in gravitationally stable regions like range points, could become the only means for future intelligent beings, human or otherwise, to recover the story of the cosmos. Organizations today, such as the Long Now Foundation and Breakthrough Starshot, are already exploring these ideas on a smaller scale. The concept of building enduring legacies, physical and digital, that can last billions of years may soon become a new scientific and ethical frontier. Philosophical implications. The knowledge that most of the universe is slipping beyond our grasp evokes deep existential and philosophical questions. What is the purpose of exploration if the universe is ultimately destined to become cold, dark, and uninhabitable? Is our pursuit of knowledge a form of cosmic resistance against entropy and isolation? Many argue that understanding the universe is an act of meaning-making, that even in a transient and impermanent cosmos, our curiosity, creativity, and resilience define our place within it. In the face of the vast and unyielding forces of nature, the very act of looking up and asking questions is a uniquely human triumph.